operating system internals course, we will be diving deep into the operating system, lifting the covers, looking inside. We'll be looking at kernel debuggers and everything else. For those who have been keeping track, Mark Russinovich used to give this talk way back. The last one, I believe, was in 2010. Just to set expectations, this is a different session from most other sessions at Ignite. We are here to talk about how we solved certain problems. This is not a session where we'll be wowing you with new capabilities or features. We are not selling anything, not marketing anything, just going deep dive. So if you're here trying to look for new insights on how your life might be easy, but most of your lives, it might not be the right session. But otherwise, this is the kind of session that I would love to attend, and I would love to be where you guys are. So again, thank you very much. Be ready for a very deep dive into the Windows kernel, looking at some of the cool things that we have done and how we have tried to solve it. I've divided up the session into roughly 2 parts. The first part, which is a very brief introduction on what is an operating system, to set the stage for 5 deep dives where we will go through developers, security, operations, and tools. So we have 5 deep dive topics. But before that, let me get started with a Wayback Machine, 1983. This was a year when Michael Jackson, interestingly, popularized the moonwalk. It was also when Star Wars Return of the Jedi came out. For those who know about the game called cricket, India, for the first time, won the World Cup. It was a big deal because that's what made that game very popular in India. And they won the next one 25 years later. But still, it was good. But more interestingly, Microsoft unveiled Windows, a graphical user interface on top of DOS in 1983. We shipped it 2 years later, but it was the beginning, a journey that we started then. I was 12, never heard of the PC, never heard of Microsoft. Life was good. But since 1983, the world has changed. Microsoft started off with the mission of having a PC in every household. I think we have pretty much done that. Microsoft no longer identifies itself as a Windows company. It does far more things. Our mission now is to enable people and organizations to achieve more. And that's very profound, and that is very interesting when you start looking at it, of how the mission statement is all about trying to get others to be awesome. Satya recently had a quote, I believe that was his quote, but I read it, that people joined Microsoft, or they was addressed to the employees, like, you joined Microsoft not to be cool, but to make others cool. And I thought that very easily and aptly sums up what we are trying to do. I've been part of the core operating system since 2006. That's a long time, and people keep asking me, like, why so long? What's there? Now, the key thing is, I get to work on some really awesome tech, and that's super cool. But more importantly, for me at least, I get to work with real down-to-earth geniuses. And I have one such person here, Arun.
Thanks for that. A little overblown. My name is Arun Kishan. I run the development for the base OS team at Microsoft. We build the common OS platform across everything, client, server, cloud, IoT, everything. I've been with the team, Matthew was saying 12 years is a long time. I've been with the same team for 16 years. I've worked on everything from XP to latest Windows 10 and all the server variants in between. So I've been there a long time. It's great stuff. We've done a lot of amazing things over the years, and I hope to show you some of that today.
Okay, and I'm Matthew John. I am a GPM, a program manager in the operating systems team. So that's us. All right, let's start with operating systems. What exactly is this, and why do we care? Why do we need an operating system? Now, this is my definition. I tried to look up Bing, I looked up Wikipedia, and they have varying degrees of this kind of information. But mainly, in my mind, stuff it does is manage hardware, essentially carve out the hardware and give it to the applications. It provides a runtime for an application so that they can keep running. It provides the necessary tooling for developers or for administrators to manage the whole thing. And then really it needs to get out of the way. But when you start adding on to it, well, there's more to it. It needs to be reliable. It just needs to keep working, and I should not have to take it downtime and so on and so forth. It needs to be performant, which means that when there is hardware available, it should be able to provide all that hardware to the applications. It should be trustworthy, and I keep hearing that word again and again and again. The operating system needs to be trustful or trustable, or whatever word you use it. Essentially, it means that please don't kill me, please don't let me screw myself up, and so on. So it's very important, that thing. But then you add on more things because there's a set of implicit expectations on what an operating system is all about, which is it needs to be serviceable. Yeah. Bugs exist, security vulnerabilities exist, so we need to be able to do that. It needs to be compatible. You need to be able to bring old stuff over, so as we keep modernizing or bringing it forward, the applications that was written way back needs to keep working. It needs to be simple, and the definition of simple keeps changing. 20 years back, what was simple is not what is accepted today as simple. It needs to be modern. So it needs to feel like what you have in your piece, in your hand, is a very nice-looking new thing. And of course, it needs to look beautiful, the operating system, the hardware, everything. And we keep evolving on these things. But the interesting question is, we've been playing around with this thing for about 30 years plus. Aren't we there yet? Are we done? Why do we have to keep modifying the operating system? And it really brings down into these 4 areas. Starting with hardware, the innovation on hardware is not stopping. In fact, it's continuing at a very exceedingly rapid pace, whether it's to miniaturize things, whether it's to make things more performant, more I/O, more processing. The industry itself is evolving. As connectivity is increasing, you have more and more connected devices. You actually can think of newer scenarios. But then you also have disconnected scenarios. And so you keep going back and forth between centralized and decentralized models. Security, it's one of those biggest threats our industry is facing. And it's not reducing, it's increasing day by day. But despite all of this, the most important thing is you. You are developers, administrators, consumers. You keep pushing us for more things. More things that only the operating system can do because it bridges the gap between hardware and the application. And you want it all. You want all of the things that I just mentioned without changing anything. Everything should just work, which is so awesome. It's conflicting, makes our life incredibly challenging, but it's awesome. I actually had an interesting quote I was looking up for some things, and let me read it out from here, from my notes. So this person was saying, I've used Microsoft products since 1996 for work and home, and I was very happy until this new Office and the new Windows came into existence. Office is hard to use, reduces productivity, and is very frustrating. It's a total failure in my opinion. Windows blah is also impossible. Can you guess which version of Windows they were talking about? Oh, come on. Vista, that's an easy one. It was Windows 7. So arguably one of the most popular operating systems when you look back and saying, whoa, that's awesome. People had this reaction when we first launched it. And we get this, and we understand this, and actually that person was probably completely true because we changed their world. Every time we bring out a new operating system, new experience, we continuously change the world. So the reason why I'm calling this out is that as engineers, our job is not to make anyone's life difficult, but to try to bridge the gap of customer expectation in terms of how do we give them the best of what's available out there, protect them, make their life easy, keep them modern and everything, life is simple, single click everything, yet continue to make them feel like things have not really changed. It's still their old familiar stuff that they're used to. So with that, today's session, we will talk about 5 different things. We'll start with some debugging and tooling. There's a conversation that we'll have about dynamic tracing, Windows Subsystem for Linux. Those are roughly for the developer tools. Talk about trust in an untrusted world. You might have heard of enclaves in some of the other sessions. We'll talk about that. We'll talk about containers. What are the underlying things or the engineering that goes behind making it happen? And then we'll talk about some cool performance things with hardware offloads with NVMe Direct and how we made that happen while maintaining trust. So with that, I have a quick question for you. Anyone guessing what the size of the Windows source code is? Throw out a number. 10 meg? 300 gig? Sorry, I didn't hear that. 300 meg? 1.4 gig. Okay, it's 500 gig or more than 500 gigs. So just an interesting tidbit. We write a lot of code. Okay, we'll start with debugging with tracing. So in my developer days, I used to love doing printfs followed by tail minus f and grep. That used to be my bread and butter. Of course, kernel debuggers and all those things are useful. But in a production environment, that was great. Like I could do printfs. Now, of course, what you start with a simple printf, you need to add on other interesting traits saying that certain modules you want to turn off debugging, other modules you want to turn on tracing, and so on. So you would introduce all these things. Unfortunately, I stopped my coding days way back in the 2003 timeframe, and I haven't done much. But that was also the time where this new technology was created by Solaris Sun, which was called dtrace. Now, some of you might be familiar with dtrace. It's a very interesting framework. It provides its own language of how to introduce add tracing to your kernel code or user mode code, and provide these trace logs that come out that you can do very interesting things. So you can turn off stuff, you can turn on or off, add timers, and so on and so forth. That simple code over there, all it's doing is measuring the time it takes to launch a process. So at the entry of the process, you take a timestamp. At the process return, like the create user process return, it's measuring the timestamp and just printing out the delta. So you can do incredibly simple or complex things with this kind of framework. And what we just did recently was introduce dtrace as part of Windows. And for that, I have Arun to talk more about it.
Thanks, Matthew. So as Matthew mentioned, we're launching dtrace as part of Windows with the upcoming release. This is derived from the FreeBSD version. All of these versions end up coming from the original Solaris or Illumos database, code base. We support 4 types of probes or trace types. FBT is function boundary trace, syscall, so system call tracing, ETW, so eventing, and profile, which allows you to take samples. The first one, FBT, is implemented through code patching, so we're actually able to dynamically instrument the code, like add code on the fly to the running system. Syscall and ETW take advantage of a new callback infrastructure, which I'll talk about in a second. And the key here is if you know dtrace or have used it somewhere before, it's the same D language and experience that we're providing. So here's a quick view of the architecture. The blue box, the CDDL license components are going to be a separate downloadable that's available from Microsoft. It contains the executable dtrace. This is the thing that actually processes the script and compiles it down to like a bytecode, which it then pushes down to the driver, dtrace.sys, which interprets that code. It implements the probes in conjunction with a system component called tracex.sys. This is a feature on demand in Windows that when you install dtrace, it will activate in the kernel. TraceX is also the thing that coordinates with user mode symbol server so that it can help resolve the symbols. So what I'm going to do next is I'm actually just going to show you how this actually works. I'm going to cut over to the demo machine here. So one of the limitations in the first version is that it will require a kernel debugger to be attached in order to enable that. We're looking at how we can relax that restriction moving forward, but in a sense, the system has to be enabled for debugging. Let me go ahead and switch to the demo machine here. Okay. How many of you have ever used or seen a kernel debugger for Windows? Okay.
All right.
It's good. So here we go. I'm going to launch a kernel debugger session just so that the dtrace VM is set up for debugging. We're not going to use that. I'm going to go ahead and start the VM. And you'll see it's connected to the debugger here. Okay, so this is actually a internal development version of the OS. It's called One Core. You may have heard about it elsewhere. So it only has a terminal. It doesn't have multiple sessions. So to do the demo, I'm actually going to have to run a telnet session to this. I'm going to run 2 telnet sessions with an extremely secure blank password. Okay. So just so I can have side-by-side windows. Having a resolution quirk here, 1 second. Okay. So I'm going to go to a demo directory here, and on this side as well. This is a little bit of a contrived demo, but it gives you a flavor. So this myapp.exe is an app that has 2 threads in it. It has a server thread and a client thread, and they're communicating with each other over name pipe in the same process. So it's not too useful, but it's helpful to kind of demonstrate some of the capabilities of dtrace. So go to run this app. I say, wow, it failed, some error. So, how do I maybe debug through that and figure out what's going on? Well, I'm going to use a dtrace script. I'm going to pull up here. So this is actually instrumenting the create name pipe file. That's a system service call underneath. So you notice here that it's scoped to myapp.exe. I'm going to start a speculation trace. On the return, if arg0, so arg0 here is the return code, and NT is a little weird. Those of you who've debugged know that 0 means success, NT success, status success. So this actually means the failure. So if it fails, I'm going to capture the trace. I'm going to further do tracing on the IO manager pads and the object manager pads. That's what these 2 are. And I'm going to specifically instrument the calls into the IO manager to complete a request. I'm going to dig into the IRP. So the IRP is the IO request packet. This is an example of how if you have symbols, you can actually cast the arguments and access the symbols. So I'm actually going to record the status of the call. And also, every time we call into a driver, I'm going to print out the driver name. So let's go ahead and run this thing. So it pauses for a minute because it's actually instrumenting all those places dynamically. So you'll see I installed almost 5,000 instrumentation points. I'm going to run this again. And so here you go. Here's the output. So if I come here, you can see going through a lot of object manager functions in the kernel. And here it goes into the IO call driver. So this is where it's going into the IO stack. You can see here, this is wrapping inconveniently, but you can see this is filter manager. And then further down here, you'll see it ends up in the SMB driver. And then you get this error code, C003. And if you go ahead and look up that error code, I'm going to use my kernel debugger to do that. Just do error C00003. That's object name invalid. So what does that mean? So if you go dig in, it actually means that we're trying to create a local name on the network, which is actually not allowed. So if you go ahead here, let me cancel the dtrace script. If I go ahead and run this again and say, hey, create a local name instead, it starts running. It works. So that was an example of how you debug that. Now if I actually want to profile this and see, hey, what's going on with the IOPS, what's the performance of this thing, I can use a script like this. This basically, at the start of the script is going to print out the, 2 columns, keeps track of the IOs and the bytes. Every time we go into write file or return from write file, we'll capture the timestamp and we'll increment these counters, and we basically aggregate the time taken for the IO. And periodically we'll print out using this profile command, what's happening for IO performance. So let me go over here. Let me do dtrace -s IO profile. There you go. So now you'll see And this printout just means it's running behind a little bit. But you can see you have roughly 15 to 16,000 IOPS here. And if I go ahead and cancel this and then cancel this, you see the distribution of latencies actually looks quite high for an in-process communication. So that seems weird. So why don't I actually profile this thing? This is a very simple D script. What I'm doing is I'm going to, in the context of myapp.exe, I'm going to aggregate stacks. Okay? So this shows you like how powerful dtrace is. Very easy. This says aggregate all stacks of a signature and how often they're occurring. Let me go ahead and run that now. So it'll just run for 10 seconds. So I'll do it again. Okay. So if you look at this aggregated all the stacks, and it showed me, hey, what's happening most frequently. If I look at these ones that are occurring quite heavily, you're seeing we're actually spending a lot of time in the networking stack for what's supposed to be a local communication. And so essentially, that's because the client is connecting through the network. It's not using a local name. So if I run the same thing again, both client and server using local names, and go back to the I/O profile. Let's give it a second here. Remember, we were in the range of 15,000 to 16,000 IOPS. Now you'll see we're in the 120 kind of range, so almost 10x. And if we go here, cancel then this, and get the latency distribution is much lower. So this gave a very contrived example of how you could use dscripts to instrument an already running system to try to root cause a problem, also profile it, and then make adjustments accordingly. So that I'm going to hand back to Matthew.
Thank you, Arun. All right. That was number one. We don't have a lot of external documentation yet on dtrace. This is one of those few things where you're actually hearing it for the first time. But then we will have, but in general, dtrace, you can go to dtrace.org and learn more about it. It's pretty powerful, whether it's Windows or non-Windows systems. All right, another tidbit. How many number of commits do you think the Windows developers do in a 6-month release cycle? 8, yes. 10 million, did someone say 10 million? 100,000, so the answer is really 4 million commits. So that's pretty, well, you were close, I guess, 2x. Maybe we should do more. But where it comes down to is that we have moved our source code to Git as well. But then imagine this 500 gig source code, 4 million commits. The time it takes to clone the whole thing, it takes 12 hours, 3 hours to check out, 8 minutes of the status, and 30 minutes to commit. That's a long time and a lot of wasted energy. And so that's where the team came up with something called the Git Virtual File System, the GVFS, which drastically or dramatically reduced this whole time it takes to do all of these operations for the large Windows source code. So we had to do this because it's one of the largest source codes ever on Git. Now, this was a plug for if you want to learn more about the engineering systems of how these massive source code projects are done, please go attend that session, BRK3365. Anyway, moving on to the next one. Continuing with the developer tools. So the other big phenomena that's going on is Linux. The popularity of Linux for the backend, for server, and everything else is skyrocketing. And we understand that as developers, they want to use Windows, and they want to use Linux utilities or GNU utilities on Windows. In the past, it was through POSIX subsystems or SIGWin or other things. But recently, we announced, like last year with Windows 10, we introduced something called the Windows Subsystem for Linux, where you could run Windows Linux executables natively with 0 modifications on Windows. That was one of the coolest things I've ever seen. Getting Linux to just run without any other magic needed. You can just download an Ubuntu image or a CentOS image or a SUSE image down and just keep executing as if it's running locally. And this was not in a virtual machine. The picture over there, I just picked it up from InfoWorld. We got the Technology of the Year award for this tech. And the 3 background screens that you see over there, the shells, are 3 Linux systems that's running natively on Windows. So effectively, you can think of it as if it's 3 different OSs or 4 different operating systems running on a single BOS without virtual machines. But how do you make that happen? And when the big challenge is there, and that's where Arun gets in and talks about how.
Okay, so NT operating system has always been designed for this notion of subsystems. If you remember way back in the early versions, we actually supported an OS2 subsystem and a POSIX subsystem. And these typically consisted of a in-proc DLL that implemented the API for that subsystem, and then a subsystem server process that was shared across all the processes in that subsystem. The intent of it was slightly different than WSL. The intent then was to be a tool to help porting software from those OSs to Windows. And it essentially required a recompile. But there were a couple challenges with this approach that we found. There's some complicated system calls in the POSIX world, like fork, where it's difficult to implement once you have NT code in the process. So these subsystems, they would still load like Windows code in the process that was implementing the shim layer. And for example, if those things create a handle or write down the thread ID or the process ID in Windows concepts, if you create a clone of that, that doesn't quite work in the Windows world. And so we had some difficulties there, and we did Band-Aids over time to try that to get to work, but it was never fully robust. And we also had this ongoing treadmill because it was a user API shim. We would have to keep up with the treadmill there, because that space churns a lot. There's lots of new libraries and facilities coming out there, and we'd have to keep up with that. So WSL, Windows Subsystem for Linux, was attempting to address that, and we had to build some OS concepts to help us solve that problem. The main innovation we introduced there is this concept of something called a Pico process. So in the middle, you see what's called a minimal process. Minimal process is just a blank address space. On the right-hand side, you have a Pico process. On the left-hand side, you have a regular Windows NT process. So in the Windows NT process, you're going to have a few address space mappings and structures that are provided by the OS in every Windows process. For example, there's this process environment block that describes a process. Every thread has a thread environment block. There's a shared data page with the kernel. There's ntdll.dll, which is the Windows version of libc. It's how everything does system calls and talks to the kernel. If you go to the Pico process, you don't have anything in the user mode address space. It's blank. And it talks instead to this driver, the Pico provider. And the Pico provider is responsible for providing system call management, exception management, and address space management. Now, it still depends on the NT kernel for core resource management functionality, like scheduling, paging, file system access, but the main interface to user mode is provided through this driver. And that's how we actually enable the Windows Subsystem for Linux to load whatever it wants in the Pico process. So we actually don't need PE files or Windows files. We actually can load ELF files in there because it doesn't matter. And when they make system calls, it's the responsibility of the Pico driver to handle that. So how does WSL look architecturally? Well, you have these blue components, which are Windows processes that actually coordinate through the LX core driver to actually start a Linux instance. And init and onwards run as Pico processes. And then you see the purple arrow between them is kind of how we do IPC between the two worlds. We support multiple instances, so you can run multiple distros in this manner through that. But the key is everything that is in the Linux instance bubble is essentially running as a Pico process, as running basically unmodified ELF binaries. So I'm going to talk briefly about system calls specifically. So if you're running a Linux app and ultimately it goes down to, like libc open, it's going to make a system call or an instruction like sysenter. Normally this would go to the NT kernel and the NT would handle it, except for Linux system calls, it doesn't know how to handle it. So it delegates that to the Pico provider. The Pico provider implements that function, and we've implemented 300 plus kind of system calls in that driver. It's still a lot, but it's a lot smaller than the number that we would have to shim up in user mode, and it's relatively stable. Linux does a pretty good job of keeping the kernel user ABI fairly stable so that software continues to run as the kernel evolves. And so as we've implemented that spec, it doesn't change much, and we have pretty high compatibility with the user mode environment. So I'm going to dive in here to a demo again. I can advance this. There we go. So again, we're going to fire up a kernel debugger for WSL. I'm going to start a WSL VM. So again, we connect it under the kernel debugger. And this is called KD, so you can also do kernel debugging through WinDBG. Our resolution is off. So I'm going to go ahead here and go in the kernel debugger, and I'm going to look for the LX core driver. So I just dumped out all the modules that are loaded in the kernel. So if I say, resolve symbols, this forces the symbols for LX core driver to get loaded. So what I want to show you here is all the system call stuff I was talking about. So if you look here, for those of you familiar with Linux, all these probably look familiar. These are all the system calls that have been implemented in the driver. I'm going to specifically show you one of them that was a challenge to implement before, which is fork. So I'm going to go back here. I ignore that. So if I go here and I run WSL, it broke into the debugger. So this is the fork system call. So if I look at, K gives me a backtrace. So if I look at what process this is in the init process. So the init process is trying to create the next process, actually calling fork. Now if you look at in the stack here, this is where it came in from user mode. I'm going to basically look at that, unassemble there. So you see, hey, this is where it's going to return. The return value from the syscall is going to be in the register RAX. It's a machine register. So if I look, 2 bytes before this, you'll see this is actually where it did the system call. Now the interesting thing here is you see it came into NT, but NT said, hey, I don't know about this as a Pico process, so immediately handed it off to LX core. Okay, so I'm going to continue stepping ahead here. Since I'm familiar with the code, I'm skipping ahead. So here now we're deep into the system call of doing the fork. You can see we're doing the clone of the individual thread. So now I'm going to step up 1 frame, allow that call to complete. And I'm going to look at the local variables here. So you see these are all the variables that are happening. This thread context one is the interesting one. So if I look at thread context, that's dump that type out, and I know that it has all the machine register fields in there, so I'm going to say, hey, what's RAX for the new thread? So it's 0. So if you know fork, the semantics are the new thread basically returns from fork, and his value is going to be 0, and the caller's value will be the child process value. And then you can see the instruction pointer is going to be the same. So if I go ahead here and look at all the processes in the system, I'll see a new init process whose parent matches this guy. And if I go look at this process, you'll see a couple things. You'll see that it's a clone process, actually, so it's a fork from the perspective of the kernel, so the address space is a copy. And this thread is going to be returning back in the same place, right, in the exact same location with the new error code. So go ahead, let that go. If I go back here, you can see, hey, I'm in WSL now, and this is full, standard WSLs, I can run various apps. So these are all now Pico processes. I'm fully in the environment, so that gives you a flavor of how this interaction works with the kernel and the LX core driver. So with that, I'm handing back to Matthew. Thanks.
Thanks, Arun. Is this interesting? Yeah. All right. Thank you. That was cool. So WSL actually has a session on Friday. if you want to learn more about how to use it in your regular life, if you have not ever played with it, I strongly encourage it. It's really cool getting Linux running on Windows 10. Switching over, another question. Some of you might have heard of it. Have you ever heard of this term drawbridge? All right, one. Thank you. Well, it's partly true. So we do a bunch of OS operating system experiments. So drawbridge is one such experiment that actually came out from MSR. And yes, it definitely did start with Pico process. So it used Pico process and created something called a library operating system, a library OS that looks like Windows, and that allowed Windows to run inside the user mode and applications run inside a single process. It was a pretty cool concept. It was also the precursor to containers. So this happened like almost a decade back that we've been working on it. And it was a point in time when we finally realized like these kind of concepts is very interesting, lightweight processes that can run applications but be fully isolated. So it's almost like the precursor to the conversation we were going to have about containers. Interestingly, drawbridge actually is used in production within Microsoft, and we are trying to actively work on moving them off of drawbridge to Hyper-V containers. It's like anything that gets consumed becomes an instant legacy. It was pretty cool. Now, containers, it's very difficult for any of you to walk by such a conference such as Ignite or any of the other IT conferences without stumbling on people talking about containers. And that's the new craze, that's the big thing. I still remember in 2014, like Arun and I and a bunch of others were having conversations with Jason Zander, Mark Russ, and a few other execs on what should be the Windows container strategy. It was one of those things you look back and say, whoa, it was such an awesome thing that we were part of that decision-making committee which says, yep, we are going to go after containers. And that is the stuff that gives you goosebumps, because that decision had a couple of things that we actually made in that meeting. Two decisions. One was, yes, we will do containers, but more importantly, we will align ourselves with the container ecosystem, the open source. So a big thing was, we are not going to go fight the system, we are going to be part of the system. So that was decision one. Decision two that we made was that while the rest of the world, especially Linux and everything else, was all focused on kernel mode isolation, we realized that was not enough from a security posture point of view. We wanted stronger hardware-based isolation for our containers. So the challenge was, we need to bring that and make that happen. And that's where we introduced this concept right on day one. We didn't name it that much, but we wanted hardware isolation with something called Hyper-V containers. Effectively, we wanted a construct in the operating system that can be managed as a container with OS-level resource guarantees, but needs to be do more. And Arun, again, trying to tell us how we achieved that.
So the Hyper-V container, the big innovation there was it kind of blurred the line between what's a process in the system and what's a virtual machine. And so we call the concept that we use for that lightweight virtual machine, lightweight VM. And so the main advantages is it gives you like OS-style resource management for the virtual machine. So you get integrated memory management, which I'll talk about. It'll give you a flexible storage model via shared file system access. And it also gives you rich scheduling features. But at the same time, it gives you all the benefits of virtualization. So you get to run an entire kernel instance in there for maximum compat. You get to have machine-style lifecycle events, so you can start, stop, pause one of these containers very easily. And it also gives you a strong boundary for security isolations if you're trying to do multi-tenant isolation. So to drill into the memory management piece, in a traditional virtual machine, so you see your host here, virtual machine. If you want to allocate memory to the virtual machine, it's no longer available to the host in a standard virtual machine. With a lightweight VM, the memory gets projected into it. The physical memory on the lightweight virtual machine is actually still a virtual memory range on the host. And so that means it's subject to all of the memory management policies that the host implements, which includes paging, compression, combining, executable image sharing, direct access execute, so DAX support, I'll talk about that, and cloning, so we can duplicate these things very easily. For storage, traditional VMs, they do VHD type access, so you do block level access from the VM goes out and goes to a file, a VHD file there on the host. With a lightweight VM, we're trying to do file-based access. So essentially, files are served from the host over SMB. So we call it vSMB, so it's a virtual SMB protocol. You can also mount host locations directly into the guest, so you get shared folders that way. But the other neat thing this lets us do is if I map something like a DLL or an executable, that gets loaded into memory on the host. You can actually project it into the container and then execute out of place in the container. So that lets you share this across multiple containers very easily, so you don't duplicate that. And you also avoid, even in a single one, doing the I/O and copying it into memory. So it gives us some pretty good efficiencies. So I'm going to now show you a little bit under the hood with how all this works. So this is going to be a little more mind-bending because we're going to do nested virtualization inside the VM. So I got the kernel debugger going.
This is where we keep our fingers crossed?
Yeah. Okay, we're connected. We're booting up this. So this VM will be the one I use to run Hyper-V containers. Hope it's somewhat legible. I'm just going to check one thing real quick. Okay. So what I'm going to do is I'm going to create a couple nano containers. So we have nano server images, which are slimmed down server images, different runtime that we use for containers. And so here you can see the command used. I'm going to create 3 of them. Okay. And the key here is the isolation equals Hyper-V is going to launch these under Hyper-V. And I'm going to go ahead and start the Docker daemon here. Let that start up. And so the key there is because this isn't a VM, those are running in isolated containers inside the VM. It's going to use nested virtualization. Okay? So that's another topic in and of itself.
Yep. Maybe next time.
So here we go. Okay, so the Docker daemon's running. So I'm going to go ahead and run this script, and I'm going to create 3 containers. So you'll see them start to spin up here. Okay, so there's the 3rd one starting up. And what I want to show you here is under the task manager, if I look at details, I go here, you see these things, the VMM. Okay, so this is the memory process. This is actually a minimal process, if you remember the concepts I talked about earlier. It's just an address space that represents the memory of the lightweight VM. The first 2 here are the template. So the first time you spin up a Hyper-V container, we pre-create the environment. The remaining 3, these are the live 3 that are running here. Those are cloned. They're actually forked off that. And so you'll see actually this is memory that's shared. You'll see that's non-zero because this includes all the executable files that are shared between those as well as the private memories that gets forked and is copied in all these. So just to give you a sense of that, if I go back to my debugger here, I'm going to dump out all processes that match the name VMM. So these are those 5. So if I look at this one, you can see, yes, it is in fact a cloned process corresponding to that. So come back here, close this, and then close these off, because now I want to, I'm going to run this PowerShell here that all it does is shut down those forcefully, just to make sure there's no remnants for the next part of this demo. There we go. Okay, and then we can just verify that they're all gone. Okay, and then I'm going to go ahead and enable debugging inside the VM. I'm going to kernel debug those lightweight VM kernels now. Okay, so this is the part that's...
Inception.
It's going to be... I'm hoping it works. Okay. So that's enabled. So now I'm going to fire up a debugger inside here. So this kernel debugger is going to attach to the nested kernel inside this thing. So now I'm going to start a server core container. So same thing, only difference is It's server core, still isolation equals Hyper-V. Go ahead and start this up. And hopefully it will connect. Wow, I'm lucky today. So it's booting up under there. I'm going to debug it from the outside once it starts up. Any minute now. There we go. So let me now step out here. So I'm going to look again for that VMM process. Here it is. Now there's only one because there's no clone this time, because when I enable debugging on this thing, the templating is disabled because the debugger connection needs to be maintained. I'm going to go ahead and dump this process out. So what I'm going to show you here is some of those memory management functions. So this VAD root, a VAD is a virtual address descriptor. So this describes all the memory ranges in this process. So there's a kernel debugger extension called bang VAD. I'm going to use that here. It dumps out a lot of stuff, so you don't need to read all that. But the key takeaway here is you see here the private memory associated with this is 1 gigabyte. So this is the 1 gigabyte of virtual memory on the host actually corresponds to the 1 gigabyte of physical memory that container thinks, that lightweight VM thinks it has. The other part I wanted to show you about this was see all these file mappings? You know, this mapped, executable, you know, WS core DLL. These are all the DLLs that actually are mapped in the host and then projected into the container as an execute in place range. So I'll show you that with a very specific example. So CSRSS is the Windows subsystem process. It's in every session. It's the first process that starts up. So you see CSRSS is here, and it's mapped executable into the container. So I'm going to go ahead and resume that. Now, we're going to get lucky. I'm going to connect to the debugger inside the container for the lightweight virtual machine. So now this is the KD for the kernel inside for the server core Hyper-V container.
Did we lose you guys yet?
Everyone
Still
with
there?
me? So I'm in the container now. This is not the host. This is the container. And I'm going to find csrss.exe because I want to show you that it actually has a execute in place mapping for the executable. It doesn't matter which one I pick. I'm just going to pick the second one. There's two because every session has its own, and there's 2 sessions in server core. Okay, so go here. Again, I'm going to look at the virtual address descriptor root for CSRSS. Okay, so one thing that you will see here, right here, this is the csrss.exe mapping, and you'll see it's actually coming over vSMB that I talked about, so the virtual SMB redirector. I'm going to look at this specific descriptor now. And you'll see here this control area. So the control area for a file mapping is what describes the pages that correspond to a file mapping in the NT kernel. So anytime you map a file in different processes, they end up sharing the same control area. So I'm going to go ahead here, and I'm going to dump out the control area flags field. And here you'll see it's using file extent. So that means it's not actually backed by real memory, it's backed by execute in place memory. So we can see that another way also, which is I can do bang control area on that same value. This gives it a little more detailed view. So again, this is corresponding to this VSMB file, right? All these subsections respond to the page table entries because we have this concept called prototype page table entries, which contain the physical pages that this thing uses. And any mapping essentially will populate its page table entries using these entries. So what I want to show you is that these physical frame numbers in here aren't real memory. They're these execute in place mappings. So I'm just going to pick one of these. So if I go here, I look at the page table entry. So this is using built-in extensions, so bang page table entry. And I see this is the page frame number. So that's the physical memory page that is used for this. So if I go look at this now, I know we're in the
Going
weeds
down
here.
the rabbit hole.
Okay, so this is the physical frame number. So I'm now going to dump this out. And you'll see that this is a file-only page frame number. It's not a real page frame number. And another way to see that is if you do memory block. This shows you all the physical pages this machine thinks it has. And you see the last page ends here, whereas this one is outside of that. So these are projected in as execute in place mappings, and they're not part of the physical memory. So that was like my really deep dive into kernel debugging hacking here, but at least you guys now have seen how this works. So hopefully that was interesting to you. So I'm going to hand it back to Matthew.
Yeah.
And it all worked, so that was lucky.
That was crazy. But the key thing is like trying to conceive of this is how we would solve that problem 2 years back or 4 years back, and then building it on a system that was not designed in 1983 or 85 or 91 to do all these things is the most amazing thing, which is the most mind-boggling thing. Anyway, so learn more about containers in general, the general sessions, there are tons of it. There are booths set up. People are all talking about containers. If you have never heard of it, please go read up. Going on, another operating system experiment, Midori or Singularity OS. Well, there you go. What do you know about that?
That was, I'm trying to remember, I know I've heard of Midori. You guys are trying to create a .NET OS.
Yeah, awesome.
And the Cosmos OS is the continuation of Midori.
I don't know about the Cosmos OS. Maybe.
He's more well connected.
He's
than I
more
am.
connected than we are. So yes, it definitely was one of those operating systems where we started from scratch, trying to figure out, can we reimagine operating systems in general? It actually had introduced this concept of software isolated processes, which meant that each process was so isolated from each other that you couldn't hack in. And the fascinating thing was these kind of experiments allow us to figure out what is possible in the general purpose operating system. And so the reason why I brought it up is it takes us to the next topic, which is all about security and trust. And here we talk about a bunch of things. When we look at from an operating system point of view, you have to think of all the different security threats that's going on. Again, there are tons of sessions around security, but the way to think about security is that attacks come from social engineering, from people, from administrators, from cloud operators, from hosters, from external sources. And the goal of the operating system or what we want to do is figure out how to protect your environment in the best possible way from all of these things. And so we have concepts that we have introduced inside in the system that allow us to provide these kind of solutions. You have heard of shielded virtual machines. We introduced enclaves last year. Azure has the Azure Confidential Computing that's built on it as well. Now, the challenge with all this is like you have to start thinking about like why do we need all these complex solutions? Why can't the kernel just be good enough and be secure enough and so on? The challenge is that the kernel has a very large surface area, whether you're talking about Windows or Linux or any of the other operating systems. It has a super large surface area. It is extensible by third party when you have third-party drivers and other things that you do not have enough control over. And finally, all the code that runs in the kernel has the same privileges. So a small hole anywhere in the kernel space pretty much removes all the things that you have put in place in terms of securing the environment. So the challenge has been, how do you provide an environment that is secure even from the kernel? And that's where, back to Arun.
So I'm going to talk briefly about virtualization-based security. How many of you have heard of this feature? Some of you, okay. So this is something that was introduced as part of Windows 10 initially. Essentially, the hypervisor introduces this notion of virtual trust levels. And the main idea is a higher numbered trust level can restrict the hardware and memory access of a lower trust level. So for example, through the second level paging mechanism, the hypervisor controls the mappings of what the OS thinks are physical pages to actual real physical pages through a second level page table. you can make memory ranges appear read-only, like physical memory ranges read-only, or not accessible at all. And likewise, you can filter MSR accesses and other hardware accesses through the hypervisor. You can see here that, right now we have two trust levels. We have VTL0, which is the one that the normal kernel and everything runs in. You have VTL1, which is a lockdown environment. You'll see there's a secure kernel that's at the bottom there. It provides a very minimal interface to provide some minimal functionality, but it's not a standalone kernel. It still relies on the host kernel for memory management, so like paging and scheduling and things like that. It's all about secret and integrity protection. The main takeaway there, before I move off that slide, is it's not really a virtual machine. You should think of it more as an alternate environment in the same virtual machine. So it's kind of like Trust Zone for ARM. If you're familiar with ARM processors, then Trust Zone is a similar alternate environment in the same virtual machine. Now, if you take this concept, you can extend it to basically create a notion of an enclave. So we've heard of hardware-backed enclaves like SGX, but with this virtualization-based security, you could do the same thing with the hypervisor. So an app can create a portion of its code and data that it loads essentially into a portion of the VTL1 address space. And this is only visible then to the hypervisor and the hardware. It's not visible to the operating system. If you think about it in the cloud context, then those enclaves are not visible to the guest OS, they're not visible to the host OS, and they're not visible to the fabric. So from a customer value prop, it has some appeal around confidentiality. So now we're going to poke around and then actually see how these enclaves work.
Yeah, I'll flip.
Thanks. All right. So I have a VM here, which is, so if you notice this, it looks a little different and it had that Hyper-V logo. This is because this is a Generation 2 VM. And because in order to use the virtualization-based security and everything, you need to be running a Generation 2 VM. So I'm going to go in here and I'm going to show you that. Can you see that? If you go here, you'll see that this thing is actually running virtualization-based security. So this VM now has the second trust level active. So if I go here, I have an app, enclave host.exe, and I have this test enclave.dll. This thing will load test enclave.dll into a virtual trust level 1, and it'll show that it's no longer accessible either to this guest, as well as it's not accessible via the kernel debugger, which is new, because normally the kernel can see everything. So I'm going to run this under a local debugger in this environment. NTSD is the command line debugger. I'm going to say enclave host.exe. So this first chance exception that you see here, that's just standard. Anytime you run the first debugger break-in, I'm going to go. You'll see here that this app, it's a test enclave. So it ends up saying, hey, there's a secret at this address that's inside the enclave. The app tries to access that and gets an access violation. So if I go here under the user mode debugger, can't see it. There's nothing that it's unmapped from the perspective of this application. So now I'm going to go in the kernel debugger. So this is on the host now. And I'm going to have to adjust my screen sizes so I can actually see it. Having some resolution difficulty here, sorry.
It's okay.
Okay. So if I look at so this is the enclave process. So I'm going to switch context to that process. So what this means is now all memory accesses are in the context of that process. So I'm going to try to enter this in DD18C0.
So what Arun is trying to do is trying to get into the enclave's memory through the kernel debugger.
Okay. So I just typed in that thing because my resolution isn't fitting it on the screen. So you can see I can't access it from the kernel debugger either. So I'm going to go ahead and I'm going to look at the virtual address descriptor for that address. I see it here. I'm using my knowledge of the data structure to dump it out here. But you can see that we do know from the host OS side that we can't access this because it is an enclave. I'm going to go ahead and resume that. Come back here. So now I'm going to run the same thing. Say, don't handle that exception. It says secret is not accessible. Go. And you can see here the result is hex 29. That's the secret. So just so we know for future reference, the secret is 29. So we're going to go ahead and quit this. I'm going to run this again, and I'm going to run it with a -debug flag. And now I'll be able to see everything. You'll say, wait, that defeats the purpose of this whole thing if I just like run this under debugger. Well, what happens is when you run an enclave with debug option, when it loads the enclave, it will ask the secure kernel, please enable debugging on this thing. The secure kernel cross-references that with the module, which is signed. Part of the signed portion of the image has to say, I enable debug. And obviously, you would never ship an enclave DLL with that enabled, but during development, you would build that in so you can actually see the thing working. So I'm going to run it now with that option. So you see, I'm going to have the initial breakpoint here. And you'll see the app took the exception, but the debugger can actually see it now. So if I go ahead and look at the secret address, I can see it now in the debugger. So if I come back here, come back to the host. Now, enclave host. See it again. So this freeze count says that this process is actually frozen under the user mode debugger. So that's what that means. So process. Okay, so switch context to that thing. And again, apologies. I'm going to just type.
So now you're trying to access that same
I'm going to access
enclave
that same memory again
from
the kernel debugger.
KD. Yep.
2F. Okay, I just typed that secret address in again, and it's still not accessible. And so you say, how come the user mode debugger can see it, but the kernel debugger can't, even with debug enabled? And the reason is the kernel debugger directly accesses physical memory. Okay, and the whole way the virtual trust levels work is it unmaps those ranges that are in the enclave. So kernel debugger can't access it. User mode debugger can't directly access physical memory. It actually makes calls to the system that says read write virtual memory. When debug is enabled, those calls actually call the secure kernel to do the read write. And because the debug is enabled, it's allowed to see it. So there we go. So if I go ahead, say don't handle this. Go ahead, and again, the secret's 29. So it shows you that under debug, everything's visible, and this all works. So that gives you a sense of how the enclave technology works and how it can be appealing for this kind of confidential computing applications. And so with that, I'm going to hand it back to Matthew.
So what you just saw is the underpinning for how we are thinking of enabling new solutions, to come up with newer solutions for existing problems that allow developers, whether it's Microsoft developers or third-party developers, to protect their secrets. So SQL recently announced that they are shipping with enclave support. Essentially, there are secrets that they have that they want to secure from everyone, and they are leveraging this kind of tech. So learn more about enclaves, Azure Confidential Computing, security in general. There are tons of sessions that's going on. I would strongly urge, of all the things that you guys should be caring about, security is one of those things where you need to be on top of what's going on from the operating system innovations point of view, how you need to be moving the ball forward in terms of how you can protect and secure your environment, whether it's securing the whole VM, whether it's securing portions of your applications, all of those things are relevant. And onwards to the final topic, the final deep dive, which is how do we get strong, awesome performance into a VM? And so NVMe is one of those few things that has blown away all the IOPS expectations or needs as well of what strong storage I/O performance is all about. When we think of NVMe, we think of this non-volatile memory attached by a PCI Express device. It has a very scalable architecture, multiple queues that allows it to give you significantly high I/O all to a physical machine. And it's built to be awesome. The challenge now is how do I get the same level of awesomeness into a virtual machine? Now the answer might be very simple, just attach it directly, pass through a device and it should just work. Well, it's easier said than done. So there needs to be a combination of AI, it needs to be connected, but at the same time it needs to be secure, because the minute you assign a device into a VM, the VM now gets to control the device, and through that device, they have the possibility of attacking the host. And so Arun, back again for the final time, I guess.
Thank you.
Deep diving into how.
Okay, so normally with para-virtualized storage with Hyper-V, we essentially have two options today. You have VHD-based access or pass-through SCSI disks. In both of these cases, effectively you'll traverse the file and storage stack in the guest, comes out to the host, and then either you directly access disk or you go through the file and storage stack again. So you're talking about traversing multiple stacks. And then you're also talking about scheduling contention, because the virtual machine and the host have to get scheduled on the same processor. And then you also have overhead related to the interrupts. So whenever you actually do the I/O, the interrupts exit into the hypervisor and then it passes it on. So if you break out the overheads that you see here when you go to really high performance I/O scenarios, you have about 20, 20, 40, so 80% total is time spent in the guest, the VM host, or the host. So VM to host meaning the VM bus traffic between the guest and the host, and then the host overheads as well. So that's a lot. And then you have 20%. If we could solve that and give a device directly to the VM, you'd still have 20% overhead because of these interrupt-based exits into the hypervisor, then forwarding it to the guest. So to solve the first one, the solution that we've been pursuing is device assignment. So you can basically give one of these high-performance disks directly to a VM. This is NVMe Direct. Now the challenge with this is there's two portions to the disk. There's an admin queue, which lets you do privileged operations like flash the firmware, and then there's the data path, which is okay to give the guest. Now in a cloud context, you don't want to let the guest have full control over the admin queue, because then you could flash firmware on there or some side effect that will live past the lifespan of the VM. And so what we've done is we've virtualized the admin queues when you do DDA, direct device assignment, so that the hypervisor is able to filter those, but then we give direct access to the data path. And this is a pretty good trade-off. So the admin accesses are a little bit slower, but they're also very rare, and the data path goes at full speed. Now for the interrupt piece that I was mentioning, this diagram kind of gives a pictorial view of some of the overheads. So you see at time T1, I take a device interrupt that actually exits into the hypervisor. Then it will inject it back. When the interrupt is acknowledged, the EOI, end of interrupt, the guest will write to a register to say, hey, I'm acknowledging this. That will exit again. So you'll see lots of this bouncing back and forth, which is the 20% overhead. So to solve that, we use some hardware extensions. So from Intel, there's some technology called APIC-V, which virtualizes the APIC. And so then those writes for EOI and any of the interrupt control rights don't exit anymore. There's also another feature called posted interrupts, which allow interrupts to be routed directly to a VM without exiting into the hypervisor. So the combination of those two completely addresses that issue. And this is supported in Server 2019. Now there's some devices, or some machines, I should say, where we don't have either of those supports. We don't have VAPIC, we don't have posted interrupts. So with these ultra high-speed devices, we can use a type of hybrid polling approach where you actually burn some CPU and effectively don't use interrupts and poll for the completions. And you can still get very high IOPS that way. And this is something we're exploring using as well. I know Linux is using this, and this is something we're looking at using in the NVMe driver in Windows as well. So I'm just going to do a quick final demo of what this looks like here. So I'm actually, for this, I'm using my Surface laptop. This is actually a device that has 1 terabyte of storage, but it actually has 2 NVMe 512 disks inside, and it uses storage spaces to create a stripe volume, which is also another interesting topic for another day. But for this demo, I'm actually assigning one of those to the guest. And so you can see here under Device Manager that this only has the Samsung device, and it has, sorry, you can see here, there's the Surface controller, but if I go under the second box here, we have an NVMe Direct device. So this has actually been set aside for assignment to a VM. So I'm going to go ahead and boot up this NVMe Direct VM that I've assigned this device to. If it logs in. There we go. So you can see here that on this PC, I have a local disk, C drive, which is a VHD file, and then we have this E volume, which is, again, the 500 gigabytes. So this is the NVMe Direct device. So again, you can see under Device Management, you can see there's a Microsoft NVMe Direct disk and the virtual VHD device. So now I'm going to come here, I'm going to go ahead and run a I/O disk speed test, give that a few seconds to finish. So this is running against the C drive. So this is actually still going to hit the NVMe disk on the host, but it's going through the VHD stack. So you're going to be seeing the impact of the overheads we were just discussing here. It takes 30 seconds, so it should be done any second now. And then we're going to run that same test against the NVMe Direct device so you can get a sense of the speed ups we get. Same hardware, but just cutting out that portion of the stack. Any minute now, any second now. There we go. Okay, and then I'm going to go ahead and start up the one against the E drive in parallel while we look at this. So here you can see some of the latencies that we're getting in milliseconds in the, up to the 75th percentile, 90th percentile. And if I come up here, these are the various metrics around the performance for the 4K IOs. So I'll just look at total IOPS here. So IO per second in this column. About 33,000 IOPS. So we'll keep that number in mind while we let this finish any second now. So here you can see a huge reduction in the latencies already compared to what we just saw. Up to 20 times less. And then if we look at total IOPS, scrolling up here, we're at 165,000. So remember, this is the same device, but just cutting out the overhead of the software stack here by directly getting into VM. So this is a huge speed up. This is a big performance thing. So that's cool. And then I'm going to show you how we kept this secure. So this is a script I'm running in the VM here that's going to try to update the firmware on that device. So here you see Microsoft NVMe disk, say OK. Now if you notice, this thing is reporting that it doesn't support firmware updates. So this is already, we filtered that request to see if I can upload the firmware to that thing. But even if you ignore that and go ahead, it's going to attempt to flash the Samsung firmware on there, and it fails saying not supported. So this is how we can provide this kind of performance to VMs and still keep it secure in a multi-tenant scenario. And so with that, I'm going to hand it back to Matthew to close us out.
Yes. All right. To learn more about this, there's actually a detailed session on how we are trying to achieve go up to 10 million IOPS in a virtual machine. There's a storage developer conference where some of our performance engineers are giving this talk. In closing, I had one code that my daughter recently texted my wife. It's like, Mom, when you're done eating, can you please feed me? She's 19. and she was a bit down under the weather, and she was up in her room just texting. I was like, whoa. But this is how we feel with our customers. Like, we love them, we get frustrated with them, but man, that's the thing that keeps us going. So that, I felt like this was like apt, and this was just last week. So the key takeaways again, the OS keeps innovating as the hardware and the industry and security and everything else keeps innovating, and you guys are the ones that drive us. We don't come out here as often describing everything else that's under the covers. As you can see, not everyone really cares enough, which is fine. It's the end product that matters. But as we think about it, why we exist.
So I just wanted to round out by saying, we're the one OS team at Microsoft that's building these innovations and thinking about all the scenarios from like client to server to cloud. And we're trying to do innovations in each space, but because we're a one OS team, we're able to take those and apply them to new scenarios. So for example, the virtualization-based security started as an enterprise client feature, but now we've brought it to server in the cloud. The containers started out as a server feature, and now it's in the cloud, and it's also a feature that we brought to client in various forms as well. So this is just some quick examples of how we've able to cross-pollinate and use our innovations across all these spectrums as one OS team in order to like make lives for our customers better.
So once again, thank you very much for your support and patience and for being here. There's a survey at the end.
Yep.
Please, we would love to get feedback to see if we need to have such a session again. So. Yes, questions.
Questions.
We'll be here.
We'll be here. Thanks, everybody.
Thank you.
The demo gods were favorable to me.